Today I will be discussing Moller polarimetry in Hall A, specifically a project using the Magneto-Optical Kerr effect to measure target polarization. So in Hall A we use a Moller polarimeter to measure beam polarization, and Moller polarimetry relies heavily on knowing the polarization of the target, and so if we can decrease the uncertainty in target polarization, then we can decrease the uncertainty in beam polarization. And so the main goal of this project was to help improve uncertainties in target polarization by analyzing target angle and alignment. In Moller polarimetry, we assume that there's normal incidence of the beam on the target, but literature has shown that even if you're 1 degree off from normal, it can introduce huge uncertainties into your target polarization. And so it's important to nail down exactly what the target angle and alignment is. And the first step to looking at this would be to show that our target is being fully polarized. So you would want to see its polarization saturate at a certain point. So to do this, we used a Kerr apparatus, which utilized the Magneto-Optical Kerr effect, and the basics of this effect are when you reflect polarized light off of a magnetized surface, that light gains a Kerr rotation and a Kerr ellipticity. So within our apparatus, we passed linearly polarized light through a photoelastic modulator, which introduced a modulating shift between two components of the polarized light. And then this light was reflected off of our iron foil within our magnetic field and then sent to 2 lock-in amplifiers. One of the lock-in amplifiers was set to the frequency that our PEM was modulating at, and the signal from this lock-in amplifier would be proportional to the ellipticity that the light gained, and then the second amplifier was set to 2F, or double the frequency of the PEM, and this would be proportional to the rotation that the light gained. Most importantly, though, the ratio of these 2 signals is directly proportional to the magnetization of the target. And so if you plot the ratio versus the B field, you should be able to show that the target is saturating and reaching full polarization. So this plot on the left is our best result, and it does look good, but then this plot on the right is the same. They're the same data, but I've zoomed into higher fields and I fit a line. And you can see that actually when we're at higher fields, where we should be fully saturated, we're still seeing an increase in polarization, or an increase of the ratio, of about 0.5% per Tesla. And that's 5 times greater than the level of precision we need to improve for Hall A. So in our opinion, this increase after we should have reached saturation is likely due to modulated interferences within the PEM. Specifically, we could show that temperature fluctuations changed our results hugely. So likely temperature fluctuations would cause optical path length variations within the PEM, which would then lead to these interferences. And these interferences would be occurring at the frequency which we were setting our lock-in amplifiers to. And so we'd be highly sensitive to any of these interferences. Essentially, unless you were able to fully temperature control at least the PEM, you can't show precise saturation of the target with this current setup. And so until you do that, you can't move on to analyzing target alignment and angle. But in the future, if you were able to saturate the target, this would be a wonderful way of reducing uncertainty for beam polarization measurements for Hall A and for future experiments.